Chapter 6, Solving Systems of Equations. Now, Section 6.1 is about systems with two variables and two equations that you're solving, and Section 6.2 is about three equations, three unknowns. So 6.1 is not even listed on your assignment sheet with no problems assigned. I have included that in the papers that I've given you in case you want to do any of those. It's completely up to you to choose some to practice. Otherwise, move on to section 6.2 and our systems of 3x3s. You just want to kind of remember how solving these work. Hopefully you learned it previously in another class, but if not, here's your chance. We're not really focusing on what we're learning in section 6.2 this chapter, but it's kind of a review of what we're going to learn in the rest of the chapter. The rest of the chapter will be involving matrices to solve these systems. And so it's good to kind of have some background on how you would do them without matrices before we start learning about the alternative. Okay, so a linear equation in two variables, x and y, is an equation of the form ax plus by equals c. A, b, and c are constants, and at least one of the coefficients a and b are not 0, otherwise your equation would not exist. So you can't just have a constant for your equation, it has to have at least one variable in there somewhere. Same idea with three variables. In this case it's using x, y, and z. It's in this type of form here where a, b, c, and d are coefficients or constants, and at least one of them is not 0 as well, so that your equation actually exists and is not just a constant value. Alright, let's look at the different situations we can get when we solve systems of equations. Okay, so we have these vocabulary words. Consistent means a system has at least one solution, so it can have one or infinitely many. Inconsistent means it has no solution. Now, we can also solve systems graphically. So I've got some pictures here to help us understand graphically what no solution actually means. If you have two intersecting lines that represent two linear equations, then where those two lines cross is the solution, the xy value that make both equations true. It's what they have in common, right? Well, if our two lines are parallel, they don't intersect, there is no solution. There's no points in common. There's no xy value that will work in both equations. So therefore, parallel lines would be no solution. Infinitely many solutions is when our two lines lie right on top of each other. They're exactly the same line, and so they have every xy value possible in common. So that is infinitely many solutions. So no solution is inconsistent, but infinite solutions is called dependent. It's also consistent because it has at least one solution. So this type of problem is called consistent dependent. Okay? One solution is just one point where they cross, and that is called consistent independent. Now, inconsistent is just a class of its own. So consistent dependent is one type of solution, consistent independent is another type of solution, and inconsistent is our no solution. So just some fancy names you're probably going to see as you go along. Alright, let's look at some different ways to solve these types of problems. We're just going to review some things you might have seen in the past. So, I feel like I'm skipping something. Solving by substitution. Nope, I'm not. It's just, here we go. So when you solve a system by substitution, you're solving one of your equations for one variable, and then you're plugging it into the other equation. You solve, then you substitute your first answer in to get your second answer. So I'm going to go ahead, you can see I've done this problem here, but I'm going to go ahead and delete this all out. And you probably haven't been able to copy this down yet, so I'll try to retype this in here in just a second. Alright, so for now, I'm going to clear this out and just do this problem with you. Okay, here we go. Use the substitution method to solve the system of equations. So we have two equations, two unknowns. We are supposed to solve one of our equations for one of the variables and then plug it into the other one. And that's called substituting. So notice how we have 2x and negative y, and we have negative 4x and positive y. If I want to solve for one of my equations, the easiest thing to do is to take the second equation and solve it as 4x minus 5. I don't have to divide by anything. I don't have to multiply by a negative. I can keep the y on the left and move everything else to the right. That just seems like the most simple thing to do. If I decide to solve for an x value, I'm going to have to divide by 2 or divide by negative 4, and then I'm going to have fractions. If I were to solve for this y value, I would probably want to move it to the right side to make it positive and move the 1 to the left so that the y is equal to everything else. Or I might want to move the 2x over here and then multiply everything by a negative 1 to turn it into a positive y value equal to whatever. So I don't know if that made sense as to why I chose this y right here, but this was just the easiest one to solve for. Okay, so we solved for one variable. Then we are going to plug that into the other equation. So since I solved the second equation, I'm going to plug it into the first equation. And when I say plug it in, that means I'm taking everything that y equals and plugging it in place of the y value. So instead of 2x minus y equals 1, we take out the minus y, and we move over the 1, oops, so minus, and we're going to replace that y value with 4x minus 5. Now be very careful, I would put it in parentheses, because you're subtracting that entire y value. So subtracting y. This is y, we're subtracting it. We have to distribute that negative through. Now remember, the 1 I just moved away because I'm taking this first equation, I'm replacing the y with this. So now let's combine terms. So I have 2x, actually I'm going to distribute it first. So then I have negative 2x equals negative 4, move the 5 to the other side, subtract it over, right? Divide both sides by negative 2, x equals 2. Now that we have that answer, we can plug it back in. So we solved for one variable, we plugged it in, we solved for one equation. Now we're going to plug answer into second equation. Now when I say first equation, second equation, that's just for this problem. It really doesn't matter which equation you start with and which one you plug into which. You get to make those decisions depending on what you think looks easiest. So since I solved for the second one, that's why I then plugged it into the first one, and now I'm taking that answer and plugging it into the second one. I mean the first one, right? Did I just lose what I was saying? Nope. Now, yeah, I said that wrong. So now you're going to plug it into the second equation that what you solved. Okay. So we can't plug it into what we were just doing because that doesn't have a y value. So we plug it into this. That's the easiest thing to do. Now I kept making mistakes, and you honestly could find the answer by plugging the x into the first equation. That would actually work. I just am going to use what I already solved for because I feel like that makes it easier. Alright, I'm trying to get it so I can actually see what I'm doing all at once, and I'm just making this smaller and smaller. So we're just going to plug our x in there. So x is 2, we're going to go 4 times 2 minus 5. So 8 minus 5 is 3, so y equals 3. That's y, right, because I was using that equation for y. So my final answer is usually given as an xy coordinate point 2, 3,